Welcome to The Explainer. Today, we're diving into a classic David versus Goliath tech story, but this time it's playing out in the cutting-edge world of massive language models. As AI agents rapidly scale up, they're practically producing a majority of the world's data at this point, a really massive problem has emerged behind the scenes. Evaluating all that agent behavior, it's becoming insanely expensive. You've got these absolute giants, the massive frontier models like GPT and Claude, doing the heavy lifting for evaluation, but you are definitely paying a premium for it. So today, we're going to look at some really groundbreaking research from LangChain Labs and Fireworks that literally flipped this entire dynamic on its head. Okay, let's just dive right into this and see how an underdog open source model pulled off a major upset.
100 times. Just think about that for a second. That is the ultimate solution we're teasing today. These researchers discovered a methodology to reduce AI agent evaluation costs by up to 100 times, depending on your trace volume, of course, without sacrificing a single ounce of frontier-level accuracy. So if your company is out there spending thousands of dollars just to evaluate how well your AI is interacting with users, this methodology drops that cost straight to the floor, all while maintaining the exact same or maybe even better analytical quality.
And that brings us to the core research question from LangChain Labs. Right now, LangSmith processes billions of tokens a day across production traces. And just as a quick refresher, a trace is simply the recorded log of an agent's reasoning and its actions. As you deploy more and more agents out into the wild, they create this overwhelming, highly expensive mountain of trace data. The dream scenario, right, is to look at every single trace, to fully understand how the system is behaving with real users. But running a massive frontier model over billions of tokens just to analyze them? Yeah, that'll completely break the bank. So the big question is, how do you cost-effectively mine the critical signals from every single interaction? All right. Section 1, Targeting Perceived Error. To actually solve this, the researchers had to narrow their focus down. They couldn't just build a magical evaluator for everything under the sun. They needed a highly specific metric to catch within those billions of tokens. And they decided to target something called perceived error. So the crucial point here is that perceived error isn't really about factual hallucination or strict objective truth. It is entirely about user frustration. Perceived error happens when a user thinks the assistant made a mistake, or when it produces something that forces the user to step in and correct it. Think about it. An agent could technically give a 100% correct answer. But if the user is frustrated by how that information was presented, yep, that's a perceived error. We are basically tracking the breakdown of the human-AI relationship. And this is exactly why this metric is so powerful. These signals are universal. Whether you're building an AI travel agent or some super complex legal document analyzer, a frustrated user acts pretty much the exact same way. We're looking for the user explicitly correcting the bot. We look for the user outright rejecting an action the agent tried to take. We look for those repeated requests, the classic, "No, I told you to format it as a table" response. Or my personal favorite, we look for the AI itself doing the walk of shame, saying, "I apologize for the confusion." These are the universal footprints of perceived error. Moving on to the next phase, building the training ground. Okay, so knowing what to look for is really only step one. LangChain and Fireworks needed to actually gather the highly specialized data required to train an open source model to act as our judge. They needed a training ground. So the researchers pulled traces from two completely distinct internal data sets. The first is Chat LangChain, which is a super technical docs Q&A agent answering deep conceptual and debugging questions about LangChain's own libraries. The second is Fleet, which is a much broader no-code tool where users create agents for a massive variety of tasks, like writing and research. The contrast here is totally deliberate. They wanted to test cross-domain evaluation. If an AI learns what user frustration looks like when a developer is deep in coding, can it recognize that exact same frustration when a marketer is trying to write a blog post? But before they could actually train the model, they had to prep the data. And their philosophy here is honestly fascinating. They filtered strictly for multi-turn traces. Why? Well, because you need a back-and-forth conversation to actually see a user react to an error. On top of that, they threw out all the behind-the-scenes tool calls and kept strictly the human and AI messages with absolutely no text trimming. Because at the end of the day, that conversational back-and-forth is where user frustration actually lives and breathes. Now, to teach our underdog model, they needed perfect ground truth labels, essentially an answer key. And they used a really rigorous multi-stage process for this. First, a panel of models judged a trace. If they all agreed, boom, great, that's the label. If they disagreed, a second panel of models reviewed the arguments to try and reach a consensus. And if they still couldn't agree,
a human annotator stepped in to manually settle the dispute. This incredibly strict pipeline revealed that 24% of the chat LangChain traces and 18% of the fleet traces contained a perceived error. And let me tell you, that perfectly labeled data is absolute pure gold for training.
Which brings us to enter the underdog, fine-tuning Qwen. With that perfect dataset ready to go, it's time to introduce our David in this story. The researchers selected Qwen 3.5/35B as their base model. They needed something cheap, open source, but fundamentally strong enough to reason over long, multi-turn conversations. Using Fireworks' managed infrastructure, they fine-tuned this Qwen model using a lightweight technique called LoRa. But here is the surprising methodology choice that makes this whole experiment so robust. They trained the Qwen model exclusively on the chat LangChain data. They completely hid the fleet dataset from it during training. This was a really strict, intentional handicap. They wanted to definitively prove if a learned judge could understand human frustration in one highly technical domain, and then successfully transfer that understanding to a completely unseen, widely varied domain.
All right, the moment we've been waiting for, the Goliath-beating results.
Now, what's really interesting about these numbers is the sheer scale of the upset. We have our fine-tuned Qwen model, right? Trained only on coding questions. Let's see how it performed against the biggest, most expensive models in the world when thrown into the completely unseen fleet dataset. Look at the baseline. The out-of-the-box base Qwen model scored an 83.2% accuracy. Okay, fine. Then we bring in the giants. GPT-5.5 comes in at 89.1%. Claude Opus, a notoriously powerful model, hits 90.2%. And then, sitting right there at the top, our fine-tuned, heavily specialized open-source model, the chat LangChain SFT, scores a 90.8%. No way, right? It outright beat Claude Opus and GPT 5.5 on completely unseen data. It generalized perfectly. This comparison completely hits the nail on the head regarding the current paradigm shift in AI evaluation. On one hand, you have frontier models, massive scale, incredible broad intelligence, but when you're evaluating billions of tokens a day, their high-volume inference costs are just paralyzing. On the flip side, you have fine-tuned open models. They're highly specialized, they achieve equal or even better accuracy on niche tasks like identifying perceived error, and most importantly, they are 10 to 100 times cheaper to run at scale. It's a total game changer. As the source material so beautifully summarizes, open models have crossed an intelligence threshold and are now strong, out-of-the-box, cost-effective classifiers for many tasks. This text upset we just walked through isn't just a neat little trick. It's genuinely a blueprint for the future. Solving continual learning in AI is going to require massive, large-scale data mining of these agent traces, and you simply cannot do that if you are paying frontier model prices for every single trace. Specialized, fine-tuned judges are absolutely the path forward. Which leaves us with this final thought for today. The playbook is out there. With the right data pipeline and fine-tuning infrastructure, you can build incredibly smart, hyper-efficient judges that actually outperform the most expensive models on the market. So as your own AI architectures scale up and generate mountains of trace data, what specialized evaluators will you build to understand them? Seriously, think about where your bottlenecks are right now and realize that the 100 times cheaper solution might just be a fine-tuned open model waiting to be trained.